Namaskar. I am Dayan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the examples on Hamiltonian formulations. Now see your example. Obtain the Homitorns equations of motions for a one-dimensional harmonic oscillator. Solution. The one-dimensional harmonic oscillator consists of a mass attached to one end of a spring and other end is fastened. Account of the elastic property of the spring. The spring exerts a force F on the body in the opposite direction. This is called restoring force. It is found that this force is proportional to the displacement of the body from its equilibrium positions. F is equal to x. F is equal to kx, where k is the spring constant and negative sign indicates that the force is opposite to the displacement. Hence, the potential energy of the particle is given by V is equal to minus integral of f dx, V is equal to integral of kx dx plus c, V is equal to kx square divided by 2 plus c, where c is constant of integration. By choosing the horizontal plane passing through the position of equilibrium as a reference level, then V is equal to 0 at x equal to 0. This gives c is equal to 0. Hence, potential energy of the particle is V is equal to 1 by 2 kx square. The kinetic energy of the one-dimensional harmonic oscillator is T is equal to 1 by 2 m x dot square. Hence, the Lagrangian of the system is L is equal to 1 by 2 mx dot square minus 1 by 2 kx square. Lagrange's equations of motion gives x double dot plus w square x is equal to 0. Therefore, w square is equal to k by m. This is the equations of motions, and w is the omega is the frequency of oscillation. The Hamiltonian H of the oscillator is defined by H is equal to x dot px minus L. H is equal to x dot px minus 1 by 2 mx dot square plus 1 by 2 kx square, where px is equal to di by L by x is equal to mx dot. X dot is equal to px divided by m. Substituting this in the above equation, we get the Hamiltonian H is equal to px square divided by 2m plus 1 by 2 kx square. Solving these Hamiltonian canonical equations of motion, we readily get the equations for as the required equations of the motion. Example 14. For a sim particle, the kinetic energy and potential energy is given by respectively T is equal to 1 by 2 mr dot square, V is equal to 1 by r 1 plus r dot divided by c square. Find the Hamiltonian H and determine whether H is equal to T plus V and whether dH by dt is equal to 0. Solution. The kinetic and potential energy of a particle are given by T is equal to 1 by 2 mr dot square, U is equal to 1 by r 1 plus r dot square divided by c square respectively. The Lagrangian function is given by L is equal to T minus V 1 by 2 mr dot square minus 1 by r 1 plus r dot square divided by c square. We see that the particle has only 1 degree of freedom and hence it has only one generalized coordinate. The generalized momentum is defined by PR is equal to del by L by del by R dot is equal to mr dot minus 2r dot divided by rc square. R dot is equal to PR rc square divided by mrc square minus 2. Thus, the corresponding Hamiltonian function is defined by H is equal to PR R dot minus L. H is equal to PR R dot minus 1 by 2 mr dot square plus 1 by R 1 plus r dot square divided by c square. Eliminating r dot between 2 and 3, we obtain the Hamiltonian H as H is equal to 1 by 2 PR square RC square divided by MRC square minus 2 plus 1 by R. Now the sum of the kinetic and potential energy is given by T plus U is equal to 1 by 2 mr dot square plus 1 by R 1 plus r dot square plus c square. Eliminating r dot between equation 2 and 5, we get T plus U is equal to 1 by 2 PR square R C square into mr c square plus 2 divided by mr c square minus 2 bracket square plus 1 by R. We see from the equation 4 and 6 that the Hamiltonian H does not represent the total energy. T plus U is not equal to H. Now differentiating equation 4 with respect to T, we get dH by dt is equal to PR dot RC square divided by MRC square minus 2 minus PR square R dot square C square divided by MRC square minus 2 square minus R dot divided by R square. PR dot is equal to R double dot into M minus 2 divided by RC square plus 2R dot square divided by R square C square. Substituting these in equation 7, simplify, we get dH by dt is equal to PR R double dot plus R dot cube divided by R square C square minus R dot divided by R square. dH by dt is not equal to 0. This shows that Hamiltonian is H is not a constant of motion. Example 15. A particle is thrown horizontally from the top of a building of height h with an initial velocity u. Write down the Hamiltonian of the problem. Show that H